go back to our problem and see what our problem was, right? So our problem was the following: min over half norm W squared such that W transpose Xi into Yi is greater than or equal to 1 for all I equals 1 to n. This was our original problem. First question is, does this min-max swap that we will do later, would it apply to our problem? It would apply, because what kind of a function is this of W? Well, this is a quadratic function of W, right? So there is a squared term, so this is quadratic in W. And what kind of functions are the constraints of W? Well, these are linear functions, linear in W. This is quadratic in W. So both F and GIs are all convex for our problem, and so we can apply the min-max swap in our case, right? So let's try to do that. But before we do that, we have to bring these guys into standard form, where GI of W is less than or equal to 0. So what is the standard form, right? So this is equivalent to 1 minus W transpose Xi into Yi is less than or equal to 0 for all I equals 1 to n. This is exactly the same as this, right? So I'm just writing this as in the form. Now this would be my GI of W, which is less than or equal to 0. Good. So what does this tell us now, right? So now this is the original problem I wanted to solve. So now I'll write the Lagrangian of W comma alpha. I'm going to write this as alpha, but then the meaning of this alpha is alpha 1, alpha 2, dot 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 alpha n, because there are n constraints for our case. So each of these constraints will have a corresponding alpha associated with it, and I'm going to think of the whole vector as I'm going to indicate it using alpha, just to declutter notation. So what is the Lagrangian going to look like? Well, I'll first write f of W, which is half norm W squared, plus it's going to be alpha 1 times G1 of W plus alpha 2 times G2 of W dot dot dot, which can be written as sum over I equals 1 to n alpha I Gi of W, but Gi of W in this case is just 1 minus W transpose Xi into Y, this quantity here, right? So this is our Lagrangian. So now what we are saying is that we can either minimize over W, maximize over alpha greater than or equal to 0, and by which I mean this just means alpha 1 greater than or equal to 0 dot 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 alpha n greater than or equal to 0. That's what this means. You want to min-max this half norm W squared plus sum over I is 1 to n alpha I 1 minus W transpose Xi Yi. This is equivalent to max over alpha greater than 0 min over W, the same thing, half norm W squared plus sum over I is 1 to n alpha I 1 minus W transpose Xi Y. It's exactly what we did in general for F and G. Now I have applied it to our problem. We still are not sure why this is going to help, but let's see why this might help. Okay, now the reason why this problem on the right hand side might help us is because of the following fact, right? So earlier we had if I give you a W, right? So if I fix a W and try to evaluate the max problem, now that is a maximization over alpha greater than or equal to 0, right? So on the other hand, in the right hand side, now if I fix an alpha greater than or equal to 0 and I try to minimization and I try to minimize this over W, now here there are absolutely no constraints on W, right? So for any fixed alpha, now this W's minimization is an unconstrained problem, which means I know how to do unconstrained minimization, right? So what I will do is I'll take the gradient of this function with respect to W, the higher order analog of derivative, and then try to set it to 0 and see what happens. I can do that, right? So let's try that for this particular problem and see what happens, right? So what I'm trying to do is I'm going to try to solve the right hand side problem. To understand the right hand side problem, let's say fix some alpha greater than or equal to 0, arbitrary alpha greater than or equal to 0, and then ask the question, well, maybe if you have 3 data points, maybe alpha is 1, 5, 7, right? So some vector that I'm just fixing, right? So arbitrarily I'm fixing some vector alpha, and then I'm asking what is minimization over W, half norm W squared plus sum over I equal to 1 to n alpha I 1 minus w transpose xi yi. What is the minimizer? What is this value going to be, right? So can I get a hold on this value? Now, because this is an unconstrained optimization over w, now I can take the derivative of this whole thing or the gradient of this with respect to w and try to set it to 0. And so that is where the minimization is going to happen. So what is the gradient of this whole thing is going to be with respect to 0? Well, the gradient will solve the following, right? So half norm w squared's gradient is just w. So that is, let me write this as w plus sum over I equals 1 to n. There is an alpha I w transpose minus w transpose xi yi's gradient is just minus xi yi with respect to w. Now this is the gradient at any w. At the optimal w, this value is going to be 0, right? Now this is for any alpha that I've given you, right? So this w star, when I say w star, this is the w star which is the best for the alpha that I gave you, right? So you pick some alpha, and with respect to that alpha, maybe I can even say this is w star alpha, just to indicate that there is a dependence on alpha here, right? So what is w star alpha then? Well, w star alpha then is going to be just sum over I equals 1 to n alpha I xi yi. Now what is this telling us? This is telling us the following, right? So we wanted to solve this max min problem right here. Now the moment I fix an alpha, the w has a functional form that depends on this alpha. And what is this functional form? The functional form is a nice functional form which just is of the form, the w that is best for the alpha that I give you is just linearly combining my data points with alpha, right? So it's just sum over I equals 1 to n alpha I xi. Well, remember what are these guys, right? So alphas are all greater than or equal to 0, that is some fixed quantity. Yi is plus or minus 1. Xi, remember, is Rd, right? So which means w star alpha is also going to be some vector in Rd, right? So if I give you alpha, then the best w is a linear combination of your data points xi yi's with alphas. That's what this is saying, right? So which means that I now have to find that alpha which is kind of which maximizes this quantity with respect to all possible alphas greater than or equal to 0. But what is this quantity? Now here we have maximize over alpha, minimize over w. There are two variables. But now what this argument is telling us is that if I fix the alpha, the best w is just a nice function of alpha, right? So it's just a linear combination using alphas, which means that I can actually find this minimum value by back substituting this value that for w in the original objective itself, right? So I can do that, right? So let me try to do that. So to find the minimizer, so what I'm going to do is I'm going to substitute back value of w star alpha in the objective, right? So we can do this. To do this, first I'll make a note that w star alpha can actually written in matrix notation as x y alpha, where x is just a matrix which has our data points as columns x1 to xn, and y is just another matrix which has our labels in as diagonal. It's a diagonal matrix. All this is 0. The labels are all in diagonal, and alpha is as usual the alpha that I actually input to this, right? So I fix some alpha, that is this alpha. So the reason why we are writing this is because it's easy to deal with matrix notation than keeping track of the sum over I and so on and so forth, right? So verify that this is exactly same as what we had earlier, right? So this sum over I alpha I xi yi is exactly same as what I've written here, right? So why? Because these two guys will multiply to x1 y1 x2 y2 in each column, and these alphas will kind of multiply each of the column, and we'll get what we want. Okay, so just to be sure, right? So this is like a D cross n matrix. This is an n cross n matrix, and this is an n cross 1 vector. So that this product will be a D cross 1 vector, which is our W, right? So let's back substitute this quantity into our original problem. The original problem was this, right? So the objective was half norm W squared plus sum over I equals 1 to n alpha I 1 minus w transpose xi yi. Now substitute w star alpha equals xy alpha into this, right? So if you do that, right, so on simplification, I am not going to do the algebra here. On simplification, we will get something that does not have w, because wherever there is w, we are substituting it as xy alpha. On simplification, what you will get is the following, right? So you will get this term is equal to alpha transpose 1 minus half xy alpha, which is our w, transpose xy alpha. This is what you would get, where 1 is just the vector of all ones. So it's an n-dimensional vector of all ones, and this is the quantity, right? So that is, which means that if I fix a value of alpha, this is what the minimization over w evaluates to, and then I want to maximize this over all possible alphas greater than or equal to 0, right? So so which means that the dual problem that we can alternatively solve is the following, right? So now maximize over alpha greater than or equal to 0 this quantity, which is alpha transpose 1 minus half. Now I'll write this, I'll open up this transpose like this, alpha transpose y transpose x transpose x y alpha. Now this is the dual problem. Dual to what? Dual to the original problem that we wanted to solve, which was minimize over w half norm w squared, such that w transpose xi into yi greater than or equal to 1. You can treat this as the primal problem. Now what I'm saying is the following, right? So I can either solve the primal problem or I can solve the dual problem. Both will give me the same answer, right? So, but the question is, what have we gained by solving the dual problem, by looking at the dual problem, right? So that is, if we have not really gained much, then why do we bother doing the dual problem at all, right? So we need to be clear what we are gaining here. So let's see what we have gained. What have we gained? Well, the first point is that the dual variable dimension, right? So if you are solving the dual problem, you are solving a problem by searching for alpha, right? So you might do again gradient based techniques to solve this, let's say, but you will search for alphas. But where are you searching for? You are searching for alpha in Rn plus, right? So Rn plus means you are searching for alpha greater than or equal to 0 in n dimension. There is one alpha I corresponding to each data point, and then you are trying to find a vector alpha in n dimension which is greater than or equal to 0. While the primal problem dimension is what? Well, in the primal problem, what am I solving? I'm trying to find a w. Where is this w? This w is in Rd. It's a d-dimensional vector that I'm searching for. I'm searching for something in d-dimensional space in the primal problem, whereas in the dual problem, I'm searching for something in the n-dimensional space. Which means that if it so happens that your d is much larger than n, then it might be better to solve the dual problem than the primal problem, because you're searching in a smaller space, so to say, right? So, and if your algorithm, for instance, if you're using a gradient based technique or something like that, which depends, whose rate of convergence depends somehow on the dimensionality of the space where you are searching for, then smaller the dimension, better will be your algorithm, and so you might be better off solving the problem in a smaller dimensional space than a larger dimensional space. But then this will be useful only if d is larger than n. D is much larger than n, right? So this is, but nevertheless, this is one good thing to note, that you can solve the problem in n dimension, the number of points dimension, as opposed to the number of feature dimension. First point. The second point is that dual constraints are easier in some sense. What do I mean by that? I mean the following, right? So here if you are solving the primal problem, you have to search for a W which satisfies these constraints, and there are n such constraints where W transpose xi yi has to be greater than or equal to 1. These are linear constraints, but still these might be slightly more complicated constraints, especially when you're doing projections onto the space that satisfies these constraints and so on. I mean, if you're doing a gradient based algorithm, you might take a gradient step, but then you might go out of this constraint space. You may want to project it back into the constraint space, where you have to have a hold on how these constraints set is and so on and so forth. Whereas in the dual problem, the constraints are super simple. It's just alpha greater than or equal to 0. It's still a constraint optimization problem, remember. You still have to do some kind of projection onto this set, but then that projection might be much easier because the space in which you are projecting is just the positive quadrant or the non-negative quadrant, right? So projections might be easier, and so the dual problem might be easier to solve again. Now, both these advantages that we are talking about comes from the fact that, by looking at this part, that one, alpha is in Rn dimension, and so it might be easier. And the second is if d is larger than n, and the second is alpha greater than or equal to 0 might be a simpler constraint to tackle than W transpose xi yi is greater than or equal to 1 for all n. However, these two are, in some sense, auxiliary benefits that we get out of this. The major benefit or the main benefit that we get by looking at the dual problem is the fact that if you stare at the dual problem, the objective of the dual problem, you will observe something very, very interesting, that the objective depends on X transpose X. Right? So the objective now depends on the dot product matrix. Right? X transpose X is a Rn cross n matrix, which is a dot product matrix which captures the dot product between every pair of data points, and immediately something should light up, right? So why is this a useful thing to do? Because the moment you have expressed your optimization problem in terms of dot product, you know what can happen, right? So we have already seen this multiple times in this course. So more importantly, dual depends on X transpose X, and so can be, now you will have to complete the sentence from whatever you've seen in this course already, and yes, and can be what can be kernelized, which means, now by looking at the primal problem, it was not at all clear that if the data was not linearly separable but then was quadratically separable, I don't know how to solve that problem because I'm looking for a line with a margin 1. Now what I'm saying is that the dual problem reveals the fact that what is really important is the dot products between the pairs of data points, and so the moment we can write the same problem as an equivalent form which depends on X transpose X, now I can replace this with some matrix K, kernel matrix K, right? So where the dot products are in some high dimensional space, and all our discussions about mapping from low dimension to high dimension and taking the dot products will apply here. That is, you can now solve the same problem in a quadratic sense or a cubic sense, or depending on what kernel you use, or a Gaussian kernel, radial basis function kernel, whatever we want, right? So you can do all that, right? So this is something that is very, very important. So these are three main advantages of solving the dual problem. So this is the first point that I wanted to make. The second point that I wanted to make is by looking at the solution W star itself, right? So the W star for the best possible alpha that we will get, right? So for alpha star is going to look like this: sum over I equals 1 to n alpha star I xi phi I, right? So which means, so why is this true? Because if you remember, whichever alpha that I fixed, right? So the W star corresponding to that is a linear combination with respect to that alpha, which means that whatever, if I solve the dual problem and I find that alpha star is the solution of the dual problem, then the W star corresponding will be of the form sum over I alpha star I xi yi, right? So that's the way it will be, because that's what we derived, right? So by taking the gradient setting it to 0. So now this says optimal W star is a linear combination of the data points, where importance of a data point is given by alpha star I for ith data point. Ith data point, right? So that's what this means, right? So for your optimal W, how much does a point xi contribute is given by the corresponding alpha I star. And if alpha I star is 0, then it means that that point does not contribute at all. And if alpha star is positive, then that point contributes something to W star. Right? So because if alpha star I star is 0, then this xi yi does not contribute to W star. So the question is then, question is where are the important points, that is points for which alpha star I is greater than 0. We know alpha I star is always going to be greater than or equal to 0 because that's the space where we are searching for, but it does not mean that they have to be always greater than 0. There might be some points for which it is 0, for some points it might be greater than 0. The question that we are asking is where are those points for which it is strictly greater than 0? Can we somehow characterize these points? That will tell us, how many points overall contribute to W star and how many points don't contribute to W star, right? So we would like to understand that.